We start our power system and operation control. Okay, so that, and then last class we have completed. So excuse me. Okay, so last class we have completed the unit 2. Okay, and then today we'll start with unit 3. So unit 3 is control of voltage and reactive power. Okay, so control of voltage and reactive power, and then today we'll see generation and absorption of reactive power. Okay, so how to generate, which device will generate and which device will observe the reactive power. And in this unit, so I feel that you all will not find it difficult, because you might have learned, or you will learn in the power electronics, some devices which will observe or generate the reactive power. So you might have started with, already you have done with synchronous condenser, will also fall under this unit. And then even SVC. Okay, so when I talk to your module tutor, it says that you have not reached this one, but SPC and all, but you will learn in the power electronics also. But you have to be mindful that, okay, there is a misconception in our students. Okay, so when they study about the reactive power devices like SPC and all, they say that it is a repetition of power electronics in power system operation and control. Actually, it is not a repetition. So in power electronics, what you will learn is, you will learn about the working principle, operation characteristic, like VI characteristic and then all. But in power system operation and control, you will not learn this. In power system and power system operation and control, you will learn how to apply this. Okay, so SPC devices to control the voltage and reactive power. Okay, so we will not learn this characteristic and then all. Okay, so you have to be mindful about this. Okay, so before, so let's see the unit outlines of unit 3. Okay, so first we'll see the generation and absorption of reactive power. So that's why I have given lecture 1, generation and absorption of reactive power. Then second, we'll see reactive power characteristic of major equipments like excitation system, generator, transformer, lines, overhead lines, cables, HVDC system. Okay, so then another one is relation between voltage, power, and reactive power. So already you know that this relation between active power, reactive power, and the voltage, which means P equal to VI cos phi, Q is equal to VI sin phi. Okay, all this you know this, so we'll not touch again. And then next we'll see methods of voltage control, how to control the voltage. Then use of type changing transformer in this voltage control and the reactive power. Then synchronous condenser, already you have learned in the machines, so similar. Okay, so application, that means to improve the power factor, so already you have learned, so we'll not touch much on synchronous condenser. Then shunt capacitors, so here in shunt capacitors we will not learn about the characteristic and then all. We may touch a little bit, but we will not learn in that detail. But we learn how this shunt capacitor can be used to control the voltage and reactive power. Then another one is static VAR compensator. Okay, so we'll see that. And then injection of reactive power, or reactive power injection, means by using these all devices, how we can inject the reactive powers. These are the unit outlines of unit 3. Okay, so now before we start about this generation and absorption of reactive power, so first let's ask to ourselves why we have to control the voltage and the reactive power flow. Okay, so why we have to control the reactive power and voltage control. Okay, first let's ask to ourselves before we start with the generation and absorption of reactive power. Okay, so first, so when we talk about the reactive power and voltage control, okay, so when we talk about the uh, reactive power and the voltage control, so first thing we have to know that for efficient and reliable operation of power system, this voltage and reactive power control has to fulfill or satisfy the these basic 3 objectives. Okay, for efficient and reliable operation of power system, there are 3 basic objectives. So first objective is voltage at the terminal of all equipment should be within this acceptable limits, which means you might have seen all the electronics good, including from mobile phone till the large electrical equipment like generator, transformer. You might have seen that in all machine, okay, including for mobile phone, it has been written that voltage V equal to 400 volt or 230 volt. It has been given there, right? So both utility equipment and customer equipment are designed. Actually, it is designed to operate at a certain voltage ratings. Example, three-phase transformer. It should work at a 400 volt. In a nameplate, it will be given. Then synchronous generator, again, it will be given. At this voltage, it should work. And then even mobile phone, okay, so very small device, including some chips, okay, so electronic chips. You might have seen that voltages. But it has to be within the acceptable range. That is the first objective of efficient and reliable operation of power system. So that's why we have to control the reactive power and voltage. Now, what it will happen if you operate outside this limit or outside the acceptable limit? So it says if you continue, okay, working this equipment on voltages outside the allowable range, which means within the acceptable limit, what it will have is it will adversely affect their performance. Means it will not give the 100% performance, which means, and then moreover it will cause damage to the equipment. Okay, so possibly there will be a cause in damage, but if it is not causing any damage also, you will not get a full efficiency or full output. It will not perform at the full output. So this is a first objectives. Then second objective is, so everybody we have already studied that we need a stable system or power system. So now this reactive power and voltage control have a significant impact on system stability. So if you are not able to control this, then you will not be able to control the stability of the system. Okay, so to enhance system stability, why we have to enhance is to maximize utilization of electrical transmission system. So we have to control the voltage and reactive power. So second, that is a second objective. Then third objective is, okay, so then third objective is this reactive power flow. If you minimize the reactive power flow, then I square R or I square X losses will reduce or will practically be minimum. Okay, it will be reduced. If reactive power flow is minimized, then its losses will also be minimum. So if losses is minimum, then what we can say is the transmission system operate efficiently, or okay, it operated efficiently. So which means these are the three objectives for controlling reactive power and voltage control. Why we have to control is for efficient and relevant operation of power system. Then these are the three objectives which we have to fulfill. Okay, that's why we are controlling this. Okay, so voltage limit should be, okay, voltages at the terminal of equipment should be within the acceptable limit. Then system, we should have a stable system. Then we should have a less losses. How it will be achieved is if we control the voltage and reactive power. Okay, so now in this power system engineering, very difficult thing is to control the voltage and reactive power by or using the appropriate equipment to control the reactive power and voltage is one of the challenging tasks in the power system engineering. Okay, so example, so it has been said here, problem of maintaining voltage within the required limit is complicated. Why it is complicated? So we know that maintaining voltage within the required limit is complicated, which means if it is 400 volt, so we are not able to keep at the 400 volt. This is a complication we face. So why it is complicated is because our power system supplies to a vast number of loads. Okay, so there are different numbers of load, and then moreover, you know that load is a dynamic, it keeps on changing, and also it is fed from the different generating units. Okay, so in Bhutan it is fine that we are supplying or fed from the hydropower, but in other countries, So hydropower, at the same time you will have from the thermal power plant, nuclear power plant. Okay, so now this is the most challenging. We are not able to keep at the required voltage limit. And moreover, when load varies, so I said that load is dynamic, which means it will keep on changing. When load varies, then reactive power requirement of transmission system also vary. Okay, it will vary. That's why we have to control, right? And then this is a challenges. Okay, so which, since reactive power cannot be transmitted, moreover, we have to know that this reactive power, unlike active power, it cannot be transmitted over a long distances. So now voltage control has to be affected by using, then this voltage has to be controlled by using a special device, okay, connected in the system. So that's why you will see that fact device and then all. Okay, so which you will learn in the power electronics, or to some extent you might have studied this also. Okay, so but whereas if you are required to control the frequency, it depends upon the active power, but this reactive power as say one of the most challenging, okay, as of now in the power system engineering. So that's why I have written here: proper selection and coordination of equipment for controlling reactive power and voltage are among the major challenges of power system engineering. Okay, so these are the some brief theory which is not mentioned in the syllabus, but this is must to start the control of reactive power and voltage. Okay, so then, so now let's see production or generation and absorption of reactive power. Which one will produce and then which one will absorb the reactive power. So before we control the voltage, we'll see that which devices will generate and which devices will absorb the reactive power. So now these are the basic. Okay, so first let's see, these are the basics devices or equipment used in the power system. First, generator. Okay, so in electrical power system, I said that till turbine it is a mechanical part, right? So after that it will be electrical. So that means synchronous generators. Starting from synchronous generator till the load end, then it will come fall under the power system network. Okay, so now in synchronous generator, okay, so this synchronous generator can either absorb or generate the reactive power. Okay, so this synchronous generator will either absorb or generate the reactive power depending on the excitation. So you know what is excitation. So in machine you have learned the different types of excitation. So depending on the excitation, this synchronous generator can either absorb or generate the reactive power. Okay, so when it will generate is, okay, so when it will generate is when it is overexcited. Okay, if it is overexcited, then it will supply the reactive power, which means it will generate the reactive power. And when it is underexcited, then it will absorb the reactive power. So which means we have to excite the generator at the required one, right? So if we generate over excited over, then it will generate reactive power. And then if EV is under excited, then it will absorb the reactive power. Okay, so now this whether to continuously supply or observe the reactive power by the synchronous generator is limited by its field current, IF, armature current, and end region heating. So what is end region heating? So we have learned in the unit 1. Okay, so this capability to continuously supply or observe reactive power will be limited by a field current of the generator, armature current, and end region heating limits. Okay, so but nowadays, what you will see is synchronous generator are normally equipped with automatic voltage regulator, AVR, which will continuously, okay, so it will adjust, okay, which will continuously adjust the excitation so as to control the armature voltage or the voltage. Okay, so nowadays, earlier days there is no AVR system, but nowadays there is a AVR. Okay, so there is voltage, automatic voltage regulator, so which will control the generation and absorption of reactive power. Okay, so which means this automatic voltage regulator will regulate the voltage, and then so beyond excitation, over excitation, or under excited. It will not go beyond over excited nor under excited because of this automatic voltage regulator. Okay, so this is some basic of generation by synchronous generator. Then other one is overhead lines. So we have in transmission system there is overhead lines. So this overhead line will also absorb or supply the reactive power, but it will depend on the load current. Okay, depending on the load current, these overhead lines will either absorb or supply the reactive power. Okay, so now at load below the natural load, we call it as a below natural load, means surge impedance. So you might have, we have learned about the surge impedance loading, SIL, right? So if the load is below this natural load, then line will produce reactive power. Okay, so this line will produce the reactive power, and then if it is above the natural load, the line will absorb the reactive power. Okay, so here we are just studying about the how it generate and observe only. Okay, so at what condition it will generate and at what condition it will observe on. So later on we'll see how to control that one. Okay, so just now we are seeing only the, okay, so then underground cables will always, okay, so it will always generate the reactive power under all operating condition. Okay, so under all operating condition, so this underground cable will generate the reactive power because why it is always generating reactive power is owing to their high capacitance, have a high natural load. So in underground cable we consider that there is a high capacitance and which have a high natural loss, so they are always loaded below that, okay, natural loss, and hence what it will do is it will generate the reactive power under all operating condition of the power system. Okay, then transformer, okay, so everybody knows about the transformer. So this transformer always, okay, it will observe reactive power regardless of their loading. Okay, whether it is heavily loaded or lightly loaded, so it will always observe the reactive power. Okay, so transformer always observe reactive power. Okay, so regardless of their loading. Okay, so now let's take example why it is always observing the reactive power at no load or light load. The shunt magnetizing reactance will predominate there. Okay, shunt magnetizing reactance will dominate, and at full load series linkage inductance effect will be predominant there. So that's why it will always observe the reactive power. Okay, so this transformer always observe the reactive power. Okay, then another loads. So normally electrical, here we are talking about the electrical loads. So load normally it will observe the reactive power. Okay, so load will normally observe the reactive power. So then, okay, so we know that a typical load bus, so if we take it about one typical load bus supplied by power system is composed of large number of devices. Okay, so in load means, so load, this composition of load will depend on day to day also. It will depend on season and it will also depend on weather condition. So every day a load will keep on changing. So that's why I always say that electrical load is dynamic. Okay, we never know which type of load it will switch on at 11 to 12, which type of load will be put off at 11 to 12. Okay, so it's a dynamic, okay, composition depending on the day, then even season. So winter different types of load may be used, summer different type of load might be used, and then weather condition also. Okay, so in rainy season they use different types of load, in sunny season sunny weather condition, so there are different types of load. So that's why we always call load is dynamics. And then this load normally it will observe the reactive power. And then you may know that if there is a load with low, okay, so if there is a load with low lagging power factor, okay, so if there is load with low lagging power factor, okay, there will be excessive drop in voltages. Okay, so there will be excessive drop in voltages in the transmission system. So if there is a excessive voltage drop, then we can say that it is uneconomical to supply the power. Okay, so which means there will be huge losses to the utility. okay, or to the service provider. So that's why you might have seen that, okay, so this industrial or industrialist consumer are normally charged for reactive power as well as active power. Okay, so this industry customer are normally charged for reactive power as well as active power, and then they give some incentive to improve the load power factor by using shunt capacitors. Okay, so if they try to improve the load power factor, then utility or service provider tries to provide some incentive. Okay, so example here in the BPC, that asks all these large consumer to have a power factor improvement facilities, right? So example, they use shunt capacitors and then they try to improve the load power factor. So if they are improving that one, and what they will do is they will try to give some incentives in terms of monetary benefit or some other benefit they will provide. Okay, so this is load normally observe the reactive power, and then other one is compensating device, which actually it is a power electronics device, will be generally it has been used either to supply or observe the reactive power. Whenever it is required reactive power, then it will be supplied by the this compensating device. Okay, so compensating device, or whenever it is required to observe the reactive power, then we will use this compensating device. Okay, so thereby it will control the reactive power balance in desired manner. Okay, so if you use this one, then we will control. So that we'll see this all compensating device, how we will use this compensating device to control the reactive and voltage control. Okay, okay, so this is just production and then okay, so this is just production and then absorption of reactive power. So are you able to get this?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, are you able to get this all thing?
Yes, sir.
Yes, sir.
Okay, so this one here in this lecture one, that's production and absorption reactive power. What you have to know is there are three objectives. Then which device will observe, which device will generate the reactive power. So you have to know this. Here we are in this lecture, we are not talking about how to control the voltage and reactive power. Okay, so here what we are doing is just we are seeing which device will observe and which device will generate the reactive power. So now if you know these devices which will generate and observe the reactive power, then we will know which type of compensating device we can choose for a transmission system. Okay, so this is just a basic on the production and absorption of reactive power. Okay, so then we'll see the next lecture. So, okay, so next lecture is regarding the okay, so next lecture is on methods of voltage control. So now we know that which device will generate and observe the reactive power. So now in this second lecture, we'll see how to control the voltage first. Okay, so methods of voltage control in a transmission line. Okay, so now you know that, okay, so some device which generate and observe the reactive power. Okay, so then control of this voltage, actually we can control the voltage level by controlling the production, absorption and flow of reactive power in the power system. Okay, so if you are able to control the production, absorption and then flow of reactive power, then we will be able to control the voltage. Okay, so now also you might have already I have explained that this generating unit or synchronous generator, normally it is provided with AVR, automatic voltage regulator, to control the voltage. How? So normally it will control the field excitation to maintain at the scheduled level, because if it is overexcited, so synchronous generator will produce, right? And if it is under excited, then it will observe the reactive power. So that's why it is provided with ABR system. But normally this control of voltage, okay, so control of the voltage is classified into 3 types. So first one is source or sink, which one will produce the reactive power, and then which one will consume or observe the reactive power. So such as shunt capacitor and shunt reactors. Okay, just I've given example like shunt capacitors, shunt reactors, and then even you will see a series capacitor also, and synchronous condenser, static var compensator. Okay, so first one, devices used for this purpose means devices used to control the voltage in a system can be classified into these 3. First one is source or sink of reactive powers, such as shunt capacitors, shunt reactors, synchronous condenser, and static var compensators, SVCS. Then second one is line reactance compensators, such as series capacitor. Then another one is regulating transformer, such as tap changing transformer and boosters. So these devices which will control the voltage is classified into 3. Okay, these 3, first one is a source or sink, second one is a line reactance compensator, then another one is transformer, regulating transformer, such as tap changing transformer and booster. So already you have learned this tap changing transformer in DC machine and transformer in second semester, second year. So you have learned about this one. So now, okay, so now let's it will not be much effect, okay, it will be a problem on you because already tap changing transformer you have learned. Okay, so now method of this voltage control. So first let's see what is meant by these shunt capacitors or reactors and series capacitor. Actually these shunt capacitors and reactors, series capacitor, it provide the passive compensation. What is mean by passive compensation now? Okay, so actually this shunt capacitor, reactors, and series capacitor will provide passive compensation. Actually there are 2 types, passive and active compensation. But this shunt capacitor and reactor, series capacitor provide the passive compensation. So because they are either permanently connected to transmission and distribution system or switch off, which means these shunt capacitor, reactors, or series capacitor will be permanently connected to the transmission and distribution system. Okay, or there will be a facility to switch off. When it is not required, it will be switch off. When it is required, it will be switch on. Okay, through a release and all. But this type of compensation is known as passive compensation. Okay, then another type like synchronous condenser and SPCs, static var compensation. So compensators provide active compensation because this reactive power observed or supplied by them is automatically adjusted so as to maintain voltage to buses which they are connected. Okay, so which means passive means it will be connected permanently, means if there is a need of reactive power, so now you will permanently connect this shunt capacitor. So don't worry about this one. So what is shunt capacitor and reactor? So we will see one by one, but this is just general explanation about just differences between passive and in active compensation. Okay, so in passive, what it will do is it will be permanently connected and there will not be automatic supply or observe of reactive power, whereas in active, so there will be a reactive power observed or supplied by them is automatically adjusted so as to maintain the voltage. So what we will do is together with the generating unit, so they will establish a voltage at a specific point in the system. Okay, so actually here you have to know the differences between passive compensation and active compensation. So in passive compensation, it will be permanently connected to the transmission and distribution system or switched, which means there is a facility to switch off and on. Okay, whereas here in the active compensation, reactive power will be either observed or supplied by them. Okay, so these devices only, but automatically it will adjust okay, for the voltages, okay, voltages of the bus. Okay, so here these two are the basic difference between active and passive compensation. So now let's see one by one now shunt reactors. First let's start with the shunt reactors. So in shunt reactors, so actually you have to be very careful from here. Now there will be differences between shunt reactors and shunt capacitors. Okay, so first we'll see shunt reactors. So in shunt reactors, what it will do is it will compensate the effects of line capacitance. Actually, this one already you have learned. Okay, so somehow you have heard, but you may not have learned as a shunt reactor. So you have heard some problem related to Ferranti effect, where receiving end voltage is greater than sending end voltage. It is not desirable, right? We don't want the receiving end voltage greater than sending end voltage. So in such case, we can use this shunt reactor and control. But how? Actually, these shunt reactors are used to compensate for the effect of line capacitance. Okay, so this transmission line, particularly to limit the voltage rise on open circuit or light load. So normally in transmission system, what we consider is if there is light load or open circuit, so it says that its capacitance will be more, right? So which means if capacitance is more, also is not a good in the transmission line, right? Which means we require a, if there is more capacitance, so it will happen a Ferranti effect. Receiving end voltage will be more than sending end voltage, which is undesirable, right? So that's why in light load, so there will be an effect of line capacitance. So to compensate that, we will use the shunt reactor. So normally this shunt reactor will be used for EHP overhead lines, which will be greater than 200 kilometer. Okay, so it will be greater than 200 kilometer, and then you know at what voltage it is known as EHP overhead lines. Already you have learned, right? You have started with electrical power transmission and generation and transmission or distribution, and then even power system stability and design you have learned. That means you will know when we will call it as EHP, extra high voltage line. But this shunt reactor normally it will be used for EHP over line which is longer than 200 kilometer. Okay, but even this shunt reactor can be used for a short line also, short overhead line also, which require a shunt reactor if the line is supplied from weak system. Which means, so if there is a weak system, example weak source, where the source is very weak, then we can use this shunt reactor to improve its performance. Because okay, so even if there is a weak source, then we require the shunt reactor to improve its generation, right? So now, as shown in figure 1, it has been written here, as shown in figure 1. So let's assume that this is a weak source. Okay, and then when far end, okay, so in this source, let's say when there is a far end, EHP lane is here 200 kilometer lane, greater than 200 kilometer. So let's assume that when far end of the line is open here, okay, so this one is open, and then capacitive line charging current, this is a capacitive line charging current ICH will flow through the large source inductance, because it will have a inductance XS, inductance reactance XS, and what it will happen is, so it will try to increase the sending end voltage, or it will rise the sending end voltage. Okay, it will rise the sending end voltage at the sending end of the line, and then, so let's assume there is a Ferranti effect. What it will have is, here you will have receiving end voltage greater than sending end voltage. Okay, so this is the causes of this Ferranti effect. So now we have not used any shunt reactor as of now here, right? So just let's say here we have a weak source, okay, and then if there is a weak source, and then on top of that, what you will do is, here we are trying to switch off the line, or so open this line. Okay, so far end, so we'll open the line. So when we open, so this capacitive line charging current flowing through this source, Okay, so flowing this source having a reactance, inductive reactance XS, will cause the rise of sending end voltage. Okay, at the sending end line, then if there is a Ferranti effect, what it will have is this receiving end voltage will be greater than sending end voltage. Okay, this is a system diagram. Okay, so I am explaining it. Then this is a Phasor diagram, which okay, you can draw this, right? A Phasor diagram. Okay, so with this one, this is a condition which we can see that. Okay, so that uh, when we switch off the far end line, okay, so this capacitive charging line charging current will flow through this inductive source or large source, which is actually it is a weak source we have considered, but through the large source inductive reactance XS, and then it will try to rise the sending end voltage, and then if there is a Ferranti effect, then it will try to increase the receiving end voltage. So this means we are not able to control this one. So now in such case, what we have to do is we have to use this shunt reactor, because it says that if the line capacitance increase, okay, capacitance increases, then we can use shunt reactors to control or limit the voltage rise. Here we have just given this example. Okay, so now okay, so once more I will explain on this. So now when here we try to switch off the line, we are assuming that this line capacitive line charging current through this large source having an inductive reactance XS will rise the voltage, sending end voltage ES, and then there is a Ferranti effect, which means definitely there will be a Ferranti effect will cause a further rise in this voltage, receiving end voltage. So in such case, how to control the voltage? Because our objective is to have a voltage within the required range. Okay, so required or acceptable limits. So now how to control this is this by using a shunt reactors. Okay, this slide is just explaining without the shunt reactor. So then here we have get a situation, then what we have to do is we have to control the voltages. Okay, so at the required or acceptable limits. So now how we will control is we will control by using a shunt reactor. So here in this case there is increase in line capacitance. Okay, so now which means if you increase the line capacitance, then receiving end voltage will be more than sending end voltage. So definitely, so this is a Ferranti effect. So now what you can say is, so now you can use a shunt reactance of sufficient size. Okay, so we can use a shunt reactance of sufficient size must be, okay, this shunt reactance of sufficient size must be permanently connected to the line to limit this. Okay, so to limit the fundamental frequency temporarily over the voltages up to 1.5 for a duration of less than 1 second. So now what it means is if you have this type of things, the Ferranti effect and all, so now we have to limit the voltages. This receiving end voltage should not be greater than 1, but over voltages we can accept up to 1.5 if you express in terms of per unit for a duration. All that is with a limited time. Okay, that duration should be less than 1 second. So you can allow the over voltages up to 1.5, but duration should be less than 1 second. So how is this will be done by connecting a line connected reactor to serve the limit of, okay, so switching over voltages means, so now you will connect this, either you will connect permanently or you can connect with using a switches. Okay, so now normally in a weak system, so towards the source we will connect a permanent line connected reactors, and then towards stronger system, because we have to submit supply from the different generating unit, right? So now in the stronger side, so normally we will use the reactor, but it can be switchable one. Okay, bus connected reactors, which means when it is not required we will switch off, when it is required only switch on. Okay, so but here weak system normally it will be permanently connected because it's not able to cope up with the stronger system. Okay, so now what you will do is, so we have known this condition, and over voltages we have to limit till 1.5. per unit, and then that too, okay, and that too for duration of less than 1 second only. So this one can be achieved by employing a shunt reactors. Okay, so now these shunt reactors, okay, so which I've explained with this diagram. Okay, so it will be either permanently connected reactor. So normally in the weak system it will be permanently connected, and in the strong system, okay, so it will be switchable. Okay, so which means whenever you require you can switch off, whenever required it can be switched on, and whenever it is not required that you can switch off. Okay, so this is how we can connect this. And then moreover in this overhead, okay, so let's assume that maintain a normal voltage under light load condition. So let's assume that there is a light load. Okay, so in under light load condition, which may be connected to ESP bus. Okay, so as shown in this, so we can directly connect it like this, or you can connect it through the figure 3, that line and transformer connected reactors. Okay, so normally you can connect it to the bus directly, or you can connect via the transformer also. Okay, so you can connect via the transformer. So first what you can say is so transformer you have already learned, but you might have learned about this transformer which has a 3 terminal, right? One is primary, another one is secondary, then another one. Okay, so you have learned that how to control the harmonics, right? There will be additional terminal which will control the harmonics. So through that terminal, which we call it as a tertiary terminal. First one is primary, secondary, and tertiary terminal. So it's it. Okay, or to the tertiary winding of an adjacent transformer as shown in figure. This concept is same. Okay, but here it has been used the transformer, here directly connecting to the bus. So whichever you find is a easy one, you can do that. Okay, so which we can achieve by, okay, so there will be some breaker. Okay, so achieve by switching reactor using circuit breaker. Okay, so this is how we can control the voltage. Okay, so you have known that during the Faraday effect, your receiving end voltage will be greater than sending end voltage. So now it is, which is undesirable. So we want the voltage within the acceptable limit. So to have within the acceptable limit, so what we have to do is we have to connect with this shunt reactor of sufficient size, which we can determine. And then we know that this voltage, over voltage, to be limited to 1.5 per unit for a duration of less than 1 second. So now how to achieve that is we have to connect these shunt reactors through, okay, there are two ways which we can connect the shunt reactor, one directly to the bus, another one using the transformer. So now in bus what you can do is, okay, so there will be two types again. Through for the weak system you can connect permanently, or the strong system switchable bus, whenever required you will put on, whenever it's not required then it will be switched off. Okay, so this is how we can control the voltage using the shunt reactors. Okay, then somewhere it has been said that even for a shorter lines we may require a shunt reactors which will be connected. There may not be a need for reactor but connected to line permanently, but sometime we may require for a shorter line which is less than 200 kilometer ESP line, we may require shunt reactors also, but in such case we may not connect it permanently. Okay, so but in such case reactor might be switchable, which means you can use a circuit breaker and then switch off. Whenever required you switch on, and whenever not required you can switch off, or either to tertiary transformer as shown here. Okay, so let's figure 4, that is a type shunt reactor. So we can use this also. Whenever you require you can put off, put on. Whenever it is not required you can put off also. But or if you require less, also type changing means you can keep on changing this position. Okay, so this position, and then you can control the voltage here. Okay, so we can either inject the reactive power to control the voltage, or you can, okay, so change this position, either increase or decrease depending on our requirement. Okay, so in some application type reactors on own voltage tap change control facilities have been used as shown in this figure. And then this shunt reactor are normally shunt reactors construction, from the construction point of view it is similar to the transformer, but it will have a single winding, okay, per phase, and then it will have an air gap and immerse in oil. Okay, so it will be either single phase or three phase. Okay, so this is how we can use a shunt reactor to control the voltage. Okay, so what do you understand by shunt reactors? Means shunt reactor, it will either observe or generate the reactive power. So whenever required, it will observe, generate the reactive power. Whenever it's not required, then it will observe the reactive power. Okay, so now before we go for next, okay, so now I will ask one question, okay, to the okay, so I will ask one question. So if, okay, so if reactive power is zero, what it will happen to the active power in the system? So can anybody can answer this? Okay, so now if reactive power is zero, what will happen to the active power? Okay, one of you can answer this. Are you able to answer this? Okay, so 10 gems, so can you answer this? If reactive power is zero, what it will happen to the active power? So because we are using shunt reactor to inject the reactive power whenever required, and then we are using shunt reactor to observe the reactive power whenever it is again required, right? So now we are trying to observe as well as generate this. If there is more reactive power, so we are trying to observe by using shunt reactor. If there is less, we are trying to inject this. So now any idea? If it is zero, is it advisable to have a reactive power zero? Paran? Okay, so what it will happen if it is more, if reactive power is zero?
There will be no power flow, no sir.
Okay, so now, so actually, so I have planned to complete more, but I will stop here, and then tomorrow, so I will ask, okay, so randomly I will ask, so please try to find out the reason, what it will happen if reactive power is set to zero. Okay, so what it will happen to the active power. Okay, so now with this, we will stop for today's session. Okay, so now only thing you have to know is how to control the voltage. So first one, we can control using shunt reactors. So now in situation I have given here, there is a Ferrand effect, which means receiving end voltage is greater than sending end voltage. Okay, so now it is not desirable. We require a voltage within the acceptable limit. That means if it is a 400 volt line or kV line, then we have to have 400 kV on, not 480, 490 or 600 or 500 kV or even less. We have to have 400 only. So now if you get more, then it is called it as a Ferrand effect. So in such case, how to control the reactive power? So we can control not reactive power, that voltage control the voltage. Now we can control by using a shunt reactors. How? So normally when this situation will occur is when there is a more line capacitance, right? If there is more line capacitance, then receiving end voltage is greater than sending end voltage. How to control is, so we have to control by using a shunt reactor. So now shunt reactor, so there are two ways which we can connect. Okay, so first one for weak system and then strong system, or there are two ways which we can connect. So directly you can connect to bus, permanently connect to the bus when there is a weak system. Means if there is a very weak system, then we can connect permanently, and if there is a strong system, we can still connect the shunt reactor but using switchable bus. Or other way to do is you can use a transformer of 3 terminals. So one will be primary, secondary, which means this will use as a stepping up or stepping down, but another terminal will be there that is known as tertiary terminal. So if you have not learned, so please try to see one of the machine book with for the okay, so which has a 3 terminal type of transformer. You try to see that machine textbook, and the one terminal normally it is for controlling the harmonics and then all. So harmonic, when you will get, so in this such type of condition you will get a harmonics. So to control that, so we can use another way to connect the shunt reactor is through using the transformer. So the here also similar to weak system will connect permanently, to strong system will connect with the switch one. Okay, this one it is fine. Okay, so this slide which I am showing now is for a short line, and then in such case we can use some other type of shunt reactor, which can be used switchable one, or you can use a type changing transformer or connected to the transformer, tertiary winding of the transformer or the EHP bus. Here what you can do is there will be on voltage step changing control facility will be there, which means if you require a more voltage, here this position can be changed and then you can control the voltage. Okay, so that's about the shunt reactors. And then tomorrow, so we'll see the shunt capacitor. So in that we'll see the differences between shunt reactors and the shunt capacitor. So when I explain about the shunt capacitor, so you will know the differences between shunt capacitors and shunt reactors. But before that, so just I will ask one question. So tomorrow when you come for the session, next class, you try to see that what it will happen if the reactive power is 0, what it will happen to the active power. Okay, so that's all for today. Okay, so that's all for today. And then tomorrow please revise that, and then also try to revise about that 3 terminal transformer. One is primary, another one is secondary, and another we call it as a tertiary. Primary and secondary, you know that it is for stepping up or down, and then all characteristics you know. But tertiary one is normally it will be used for harmonics and then other type, like which we are trying to control the voltage. Okay, so that's all for today. Okay, thank you for coming online.
Thank you, sir. Thank you, sir.
Thank you, sir.
Okay, so thank you very much for coming online, and then please study. Okay, so now it's not like school they said it is not compulsory, but ours is. Okay, so since it has been provided with stipend and then all the theory part, it has to be completed online only. Rest, whenever you come here, we will do that. But if there is doubt, definitely we will solve when you come here also. But we cannot go like normal session. Okay, so clearing doubt. So you may say that from unit 3, this is a doubt we face. So then I will come in a class and then we'll try to clear the doubt on this. Okay, so that's all. Okay, so thank you.
Thank you, sir.
Thank you, sir.